All right, so the next section we're working on is section 4.2, which is about inverse Laplace transforms and how they help us solve ODEs. So just as a reminder, this section we're going to do after exploring Laplace transforms in class. So if you're watching this right after your exam, just like last time, I don't want you to have to watch a video like the night after you do an exam. So we're just going to work on section 4.1 in class right after your exam, and then this video is for after that. So please don't try to prepare this right away. But if you're watching this like after we've already done that exercise, great, you're right on track. So what we're going to do is we're going to look at some linearity examples for the inverse Laplace transform, just because that's the trickier direction to apply linearity. And then we'll talk about the derivative rule for Laplace transforms, how that helps us solve initial value problems, and then we'll do some examples. So just to sort of recall a bit of information about Laplace transforms. We learned about the Laplace transform, indicated by L of f of t equal to capital F of s for some function f of t. So we learned how to compute that directly, and we can also indicate this relationship in terms of the inverse, well, we'll say using the inverse Laplace transform. In which case we'd write that whereas the Laplace of little f is big F, the inverse Laplace of big F is little f. And the Laplace transform is something that moves us between that domain of t's and s's. And then an important fact is both are linear. So L of alpha f plus beta g is equal to alpha f plus beta g. And inverse Laplace of alpha f plus beta g is also equal to alpha f plus beta g, just in those different domains. And that linearity is going to be important a lot. So you should be comfortable using it. Oh gosh. Okay. Should be comfortable using it in either direction because it'll come up often. And I think that the forward direction tends to be easier than the backward direction. So we're just going to do a couple examples. This is section 4.2.1's example. And we're just going to look at computing the inverse Laplace transform of 1 over s to the fifth. And to do this, we're going to have to remember some stuff from our Laplace transform tables that should be somewhere handy in your notes because we'll use those a lot too. But the inverse Laplace transform of n factorial over s to the n plus 1 is equal to t to the n for, for n equal 1, 2, so on and so forth. So since we have s to the fifth appearing for us, n plus 1 being 5 would mean that n is equal to 4 in that formula. So if we have something like 1 over s to the fifth, it means that we plugged in n equals 4 to that inverse Laplace table. So we know that L inverse of n factorial over s to the n plus 1 for n equal 4 would be L inverse of 4 times 3 times 2 times 1 over s to the 4 plus 1, which would be L inverse of 24 over s to the fifth. And so if we were trying to take L inverse of 24 over s to the fifth, our inverse Laplace table would tell us that that's just t to the fourth. But we want to find L inverse of 1 over s to the fifth, not 24 over s to the fifth. So, we need L inverse of 1 over s to the fifth. But L inverse of 1 over s to the fifth would be the same as 24 over s to the fifth divided by 24. Those 24s canceling out right there. And so this is where linearity comes in. We would say, okay, that's 1 over 24 L inverse of 24 over s to the fifth by linearity. And then we can just plug in L inverse of 24 over s to the fifth, which we just found. So we would say that's 1 over 24 times t to the fourth by L inverse of 4 factorial over s to the 4 plus 1. And that would be the answer for the inverse Laplace transform we were trying to take right there. We'll do, I guess, one more example just to make sure that this really sticks. So 4.2.2, we're looking for L inverse of minus 2s plus 6 over s squared plus 4. And we're looking at something that has something like s squared plus k squared in it. So let's kind of write down our two inverse Laplaces that we know that involve those terms. So note, L inverse of, let's see, k over s squared plus k squared would give us sine of kt. And L inverse of s over s squared plus k squared would give us cosine of kt. So those also would come from that table of inverse Laplace transforms that you should be referring to regularly. So we see s squared plus 4 in the thing that we want to take the Laplace transform of. So that means that k squared is equal to 4. So that means that k is equal to 2. So we need terms that look like, L inverse of 2 over s squared plus 4 or L inverse of s over s squared plus 4. Then we would know that it's sine of 2t or cosine of 2t. Oops, I wanted the undo button, not the backwards button. And now that's not available to me. That's okay. So let's go ahead and try to use linearity to make that happen. We've got L inverse of minus 2s plus 6 over s squared plus 4. So that's going to be L inverse of minus 2s over s squared plus 4 plus 6 over s squared plus 4. You can always break apart things that are on top of a fraction that way. You couldn't do it with things that are on the bottom. And then I want it to have either s on top alone or 2 on top alone. So I'm going to go ahead and say that this would be equal to L inverse of minus 2 times s over s squared plus 4 plus 3 times 2 over s squared plus 4. And so by linearity, that's going to be minus 2 L inverse of s over s squared plus 4 plus 3 L inverse of 2 over s squared plus 4 by linearity. These steps right here were just algebra. And so from our inverse Laplace transform table, we know that this is going to be minus 2. L inverse of s over s squared plus 4 is just going to be cosine of 2t. Plus 3 L inverse of 2 over s squared plus 4 is just going to be sine of 2t. And that would be our answer.